Every piece of software you interact with, from the operating system booting up your machine to the browser you are using right now, relies on an invisible engine. Some applications feel impossibly fast, responding instantly to your commands, while others lag, stutter, and frustrate. It is not always about the hardware. Often, it is about the fundamental language powering that software. Today, you are going to discover exactly why C++ is that engine. The core reason it powers the world's most demanding applications, from game engines pushing millions of polygons per second to the financial trading platforms executing billions of dollars in milliseconds. No other language quite matches C++'s unique blend of raw speed and expressive power. When I first started, I thought all programming languages were essentially the same under the hood, just different syntax. I was wrong. C++ gives you a level of control that is almost unparalleled, letting you dictate precisely how your program interacts with the hardware. This control is what unlocks that incredible performance, but it also introduces a new set of responsibilities. We are going to demystify that today. By the end of this lesson, you will be able to articulate the core problem programming solves for computers. You will trace the 4 distinct stages of the C++ compilation process, identifying the intermediate artifacts like the .i and .o files that are generated along the way. We will then dive into C++'s zero overhead principle and its profound implications for runtime performance. Finally, you will learn to identify and resolve the common C++ compilation and linking errors that every developer, including myself, has spent hours debugging. Let us start with the fundamental question. What problem does programming actually solve? Imagine you have a brilliant chef in your kitchen, but this chef only understands precise, single-step instructions, and only in binary. You cannot tell them make a lasagna. You have to say take the pan, then put the pan on the stove, then turn the heat to 101000, and so on, all in sequences of ones and zeros. That chef is your computer's CPU. Programming is like writing a complex, human-readable recipe, say, in Italian, that a specialized translator then converts into those precise binary instructions for the chef. That human-readable recipe is your C++ code. The translator is the compiler. At its lowest level, a computer understands only machine code, raw sequences of binary digits like 010010011011001 that represent direct instructions for the processor, telling it to add 2 numbers, fetch data from memory address 0x7FFE1234, or jump to a different instruction. Writing those binary sequences directly is incredibly tedious, prone to errors, and nearly impossible for anything beyond the simplest tasks. Programming languages exist to bridge this gap. They provide a structured, human-readable notation for expressing computations. The core problem programming solves is the need to automate complex, repetitive, or high-speed tasks that humans simply cannot perform manually. Without programming, computers would be inert silicon and metal. They would not do anything useful. Now that you understand why programming exists, let us look at how C++ specifically turns your human-readable instructions into something the machine can execute. This is the C++ compilation process, and it is a multi-stage journey. Think of it like a sophisticated factory assembly line. Raw materials, your source code, go in one end, and a finished, executable program comes out the other, passing through several specialized stations. The entire process starts with your source code files, typically ending in .cpp or .h. These are your translation units. A translation unit is essentially a single .cpp file after it has been preprocessed. When I say preprocessed, I am talking about the very first stage, the preprocessor. This tool handles directives like #include, which literally paste the contents of another file into your current one, and #define, which performs text substitutions. It is a simple text manipulator, not a language parser. For example, if you have a main.cpp file that includes iostream, the preprocessor will take the entire content of iostream and insert it directly into your main.cpp. The output of the preprocessor is an intermediate file, often ending in .i. This .i file contains all your code, plus all the included header files, with all macros expanded. It is a single, massive file ready for the next stage. Next comes the compiler itself. This is where the real magic happens. The compiler takes that preprocessed .i file and translates it into assembly code. Assembly code is a human-readable representation of machine code, specific to your CPU architecture. It is still very low level, dealing with registers and memory addresses directly, but it uses mnemonics like MOV for move or ADD for add, instead of raw binary. The output of this stage is an assembly file, typically with a.s extension. After the compiler, we have the assembler. The assembler takes the assembly code from the .s file and translates it into actual machine code. those sequences of binary digits the CPU understands. This machine code is packaged into an object file, which usually has a .o extension on Linux or .obj on Windows. An object file contains machine code for your specific translation unit, but it is not yet an executable program. It might contain references to functions or variables that are defined in other object files or libraries. The final stage is the linker. The linker takes all your object files, along with any precompiled libraries you are using, like the standard C++ library for input-output, and resolves all those external references. It stitches everything together into a single, cohesive executable program. If your program calls a function like std::cout operator, the linker finds the machine code for that function in the standard library and incorporates it. The output is your final executable, often named a.out on Linux or .exe on Windows. So, to recap the journey, your source.cpp goes to the preprocessor, becoming source.i. That goes to the compiler, becoming source.s. Then the assembler turns it into source.o. Finally, the linker combines source.o with other .o files and libraries to create your executable. Understanding these stages is crucial for debugging, especially when you run into those cryptic linker errors. This is where it gets interesting. C++'s zero overhead principle. This is a core philosophy of the language, stating that you only pay for what you use. If you do not use a particular feature, it should not impose any runtime cost on your program. This is a fundamental differentiator from many other languages. For instance, C++ does not have a mandatory garbage collector running in the background, constantly pausing your program to clean up memory. If you do not explicitly use smart pointers or other memory management tools, you manage memory yourself, with zero runtime overhead from an automated system. This principle extends to almost every feature. When you use classes, templates, or exceptions, the compiler works incredibly hard to generate machine code that is as efficient as if you had written it by hand in C. There are no hidden virtual machine layers, no mandatory runtime checks unless you explicitly enable them, and no implicit conversions that might slow things down. This direct mapping to hardware, combined with powerful abstractions that compile away to nothing, is why C++ excels in performance-critical domains. Now, let us talk about common compilation and linking errors. You are going to run into these, I guarantee it. When I first started, these error messages felt like reading ancient hieroglyphs. But once you understand the compilation pipeline, they make perfect sense. First, a common compiler error. This happens when the compiler cannot understand your code, usually due to syntax issues or undeclared identifiers. Let us look at a broken example. Here is some code that will fail to compile. I am trying to print hello, C++ to the console. Notice the missing include and namespace. This line, cout, hello, C++, attempts to use cout, but the compiler has no idea what cout is. It has not seen its declaration because we forgot to include the necessary header file, iostream, which defines cout as part of the standard library. When you try to compile this, you will get an error message similar to this. Error, use of undeclared identifier cout. This tells you exactly what is wrong. Cout was used, but never declared. The compiler stopped right there. It cannot proceed because it does not know how to translate cout into machine instructions. The fix is to provide the declaration by including the correct header and specifying the namespace. To fix this, we add #include iostream at the top, which brings in the declarations for input-output streams. Then, we add, using namespace std, to tell the compiler that when we say cout, we mean the one from the standard namespace. Alternatively, you could write std::cout directly. Now, the compiler knows exactly what cout is, and it can successfully translate this line into assembly and then machine code. When you run this corrected code, it prints, hello, C++ to your console. Now, a linker error. These are trickier because the compiler might have successfully translated your code into an object file, but the linker cannot find all the pieces needed to build the final executable. Imagine you have a recipe that calls for secret sauce, but the secret sauce is defined in a completely different cookbook that you forgot to bring to the kitchen. The compiler knows you need secret sauce, but the linker cannot find its actual instructions. Consider this scenario. I have a main.cpp file that declares a function extern_int calculate_sum, int a, int b. The extern keyword tells the compiler that calculate_sum exists somewhere else, so the compiler is happy. It generates an object file for main.cpp. But I forgot to actually define calculate_sum in another .cpp file, or I forgot to link that other file. The linker will look for the actual machine code instructions for calculate_sum and come up empty. When you try to link this, you will see an error like undefined reference to calculate_sum, int. This means the linker found a reference to calculate_sum but could not find its definition, its actual implementation. The compiler was fine because it only needed the declaration. The linker needs the concrete machine code. The fix is to provide the definition of calculate_sum in another translation unit, say math.cpp, and then ensure both main.o and math.o are passed to the linker. Here's the fix. We create a separate file, math.cpp, which contains the actual definition of calculate_sum. This function takes two integers, 10 and 32, adds them, and returns 42. Now, when you compile main.cpp to main.o and math.cpp to math.o, and then link both main.o and math.o together, the linker finds the definition for calculate_sum in math.o. It successfully combines everything, and your program runs, printing, the sum is 42. Understanding the difference between these two error types will save you countless hours. You now understand three critical things about C++. First, you can articulate that programming solves the problem of translating human logic into precise, binary machine instructions that a CPU can execute. Second, you can trace the four distinct stages of the C++ compilation process: preprocessor, compiler, assembler, and linker, and identify their intermediate outputs like .i, .s, and .o files. Third, you grasp C++'s zero overhead principle, knowing that you only pay for the features you explicitly use, leading to unparalleled performance. Next time, we get our hands dirty with the actual building blocks of every program, setting up your C++ environment. We will get you ready to write your first lines of C++ code.